Expecting you went through that dull opening, you would appear at one more universe. There is at this point a connection between quantum handling and faint openings. In this enlightening video, we investigate an imperative and surprising disclosure made by the James Webb Space Telescope inside a faint opening, made feeling of by truth be told Bill Nye the Science Fellow. A faint opening is a star so enormous that beyond question even light can't escape from it due to its enormous gravity. The secrets of faint openings have confused experts for a long time. At any rate, at this point, by prudence of astonishing cutoff points, we've seen something genuinely staggering. The incredibly huge dull opening consumes what could be diverged from one Earth consistently. The wavering and influential first picture of a faint opening in space prepares us as we plunge into the inconceivable subtleties of this unending openness and how it might affect how we could interpret the universe. Stars, around the fulfillment of their life, much more extraordinary and tremendous than the sun, run out of fuel and start to separate as gravity squashes them. Faint openings are entrancing to recall. It was, as a matter of reality, a test to look for the starting one. No matter what the way that Einstein's theory of relativity expected they were ordinary, dissimilar to stars, faint openings emanate no light through their own effort. Their size and turn are the main quantifiable properties. We have visual check of faint openings confirming their existence, which has as of late opened up. At any rate, definitive insistence of faint openings was missing from here onward, indefinitely quite a while. The first faint opening, Sagittarius X1, was seen in 1964, yet it expected north of 30 years for specialists like Stephen Hawking and Kip Thorne to settle on whether Sagittarius X1 was without a doubt a faint opening. Hawking, a perceptible figure in faint, made sure about their open assessment presence. However, they were mindful about the deficiency of authoritative disclosures. Hawking and Thorne were practically 100% sure that Sagittarius X1 was a faint opening in 1975 when the bet was first cast, and by 1988 they were 95% certain. Still, they hung on until 1990 to regard check when more perceptions gave agreeable confirmation. The start discovery of Sagittarius X1 was made utilizing two Geiger counters sent into space on a suborbital rocket, identifying a signal pinpointed to a framework 7,200 light-years away. The framework featured a blue, extremely Goliath star orbiting another monster object, areas of strength for discharging beams, which would seem okay on the off chance that it were a faint opening. A lot of assessment has zeroed in on Sagittarius X1 since its revelation, uncovering that it is on various occasions the mass of the Sun, making it the biggest known heavenly mass faint opening found without gravitational waves. This revelation challenges long-held thoughts about faint opening turn of events and the mass misfortune experienced by stars over their lifetimes. Sagittarius X1 breaks records in extra ways than one. Its wonderful mass and the quickest turn speed of any faint opening saw up as of recently, advancing toward the speed of light, go against the acknowledged example of faint opening turn of events. Albeit conclusive proof of faint openings has as it were as of late been found, it is progressively clear that they are dissipated all through the universe. Regardless, expecting examiners at last unravel every one of the secrets of Sagittarius X1, the first of its sort, interminable others actually hold a tremendous number of shocks. Under 2,000 light-years from Earth, experts have seen as a torpid monster the Smoothway's biggest heavenly mass faint opening, Gaia BH3, with a mass a few times more noteworthy than that of our Sun. Notwithstanding being the second closest known faint opening to Earth, Gaia BH3 stayed unnoticeable until as of late. Gaia BH3 was found inadvertently while researchers from the European Space Agency assessed data from the Gaia mission, which guides our universe in 3D. The disclosure of this torpid faint opening, which isn't effectively siphoning energy and material from a buddy star, was a finished shock. Typically, heavenly mass faint openings in our Smoothway have a mass a few times that of the Sun, with Sagittarius X1 holding the record at multiple times the Sun's mass. Anyway, Gaia BH3, with a mass of 33 Sun-based masses, is still little contrasted with all faint openings. For instance, the focal very gigantic faint opening in our world, Sagittarius A*, is 4 million times more noteworthy than the Sun. Gaia BH3 is the second closest faint opening to Earth, behind just Gaia BH1, which is 1,500 light-years away and has a few times the mass of the Sun. cosmologists now have more proof to figure out how heavenly mass faint openings structure. Faint openings from the finish of enormous stars with lower centralizations of weighty metals are accepted to be the wellspring of these colossal heavenly mass faint openings. These metal-poor stars, made principally of hydrogen and helium, are thought to experience more slow mass misfortune, leaving more material accessible to shape enormous faint openings when they bite the dust. Utilizing the James Webb Space Telescope, JWST, experts have viewed as an extraordinarily red, exceptionally enormous faint opening existing in the early universe's shadow. As the universe extended, the very monstrous faint opening took on a ruddy tone. 700 million years after the huge explosion, the light going toward us is redshifted, recommending a thick layer of gas and residue encompassing the faint opening. Lucas P. Fennell and A.V. Bend of the School of the NAS Cosmology Bunch decided the faint opening's mass utilizing JWST information, viewing it as around 40 times the Sun's mass. This revelation stands apart from the universe it occupies, showing that the exceptionally enormous faint opening is rapidly consuming the encompassing residue and gas. Situated about 12.9 billion light-years from Earth, the discoveries made by the James Webb Space Telescope, JWST, have deepened our understanding of the role of supermassive black holes, SMBHs, in the evolution of galaxies. One of the most intriguing aspects of these discoveries is the way these black holes seem to influence their surrounding environments. The immense gravitational pull of SMBHs can alter the formation of stars, as well as the distribution of matter within galaxies. This dynamic relationship between black holes and galaxies challenges previous theories that suggested galaxies and their central black holes evolved independently. Researchers are now exploring how SMBHs grow and evolve over time. The JWST's ability to observe the distant past has provided critical insights into how these black holes may have formed in the early universe, possibly through the direct collapse of massive gas clouds or from the merger of smaller black holes. Additionally, the detection of quasars powered by these supermassive black holes offers a glimpse into the extreme conditions present in the early cosmos, where black holes were not only growing rapidly but also influencing their host galaxies through powerful radiation and winds. The JWST has also revealed more about the relationship between SMBHs and their host galaxies. In some cases, the growth of the black hole is thought to be linked to the rate of star formation in the galaxy. In others, the energy emitted by the black hole may be responsible for quenching star formation, effectively halting the growth of the galaxy. This feedback mechanism, where the black hole's activity affects the surrounding galaxy, is a key area of study, as it helps explain the observed sizes and shapes of galaxies across the universe. The latest findings also highlight the surprising diversity of supermassive black holes, particularly in the early universe. Some black holes appear to be growing at an unprecedented rate, while others seem to be more dormant. This variation may be tied to the availability of material in the surrounding environment, as well as the specific conditions present in the early universe, such as the density of gas and the influence of dark matter. These discoveries have profound implications for our understanding of the cosmos. They suggest that the formation and growth of supermassive black holes are closely intertwined with the evolution of galaxies, and that the early universe was a much more dynamic and complex place than previously thought. As JWST continues to explore the distant past, astronomers expect to uncover even more surprising details about the origins of these cosmic giants and their role in shaping the universe as we know it. As the James Webb Space Telescope, JWST, continues its exploration of the distant universe, it is revealing more about the early stages of galaxy and black hole formation. One of the most significant findings is the discovery of black holes that formed just a few 100 million years after the Big Bang, challenging existing theories about how these massive objects could have grown so quickly. The fact that these supermassive black holes were able to form and grow in such a short period of time suggests that they may have formed through processes that are not yet fully understood, possibly involving the direct collapse of gas clouds or the merging of smaller black holes. These early black holes are not only intriguing because of their rapid growth, but also because of their role in the formation of the first galaxies. The energy and radiation emitted by these black holes likely played a crucial role in shaping the surrounding gas and dust, influencing the formation of stars and galaxies. This process, known as feedback, can either promote or inhibit star formation depending on the amount of energy released by the black hole. In some cases, the intense radiation from the black hole can heat up the surrounding gas, preventing it from cooling and collapsing to form new stars. In other cases, the black hole's energy can trigger star formation by compressing nearby gas clouds. The interaction between black holes and their host galaxies is a complex and ongoing area of research. The JWST's observations of these early black holes have provided new insights into how they grow and evolve, as well as how they influence the galaxies around them. For example, some of the earliest galaxies observed by JWST appear to have been significantly altered by the presence of a supermassive black hole at their center. These galaxies exhibit unusual properties, such as an absence of star formation or an unusually high concentration of gas and dust, which may be the result of the black hole's influence. The discovery of these early supermassive black holes also raises important questions about the role of dark matter in their formation. Dark matter, which makes up a significant portion of the universe's mass, is thought to play a key role in the formation of galaxies and black holes. Some researchers believe that dark matter may have provided the necessary conditions for the formation of these massive objects by helping to concentrate gas in certain regions of space. The JWST's ability to observe the distribution of dark matter in the early universe could provide crucial clues about the connection between dark matter and the formation of supermassive black holes. In addition to studying the formation and growth of black holes, the JWST is also providing valuable insights into the evolution of the universe itself. By observing the light from distant galaxies and quasars, scientists can learn more about the conditions that existed in the early universe, just a few 100 million years after the Big Bang. This information is helping to refine our understanding of cosmic history, particularly the processes that led to the formation of galaxies, stars, and black holes. As the JWST continues to gather data, astronomers are uncovering more about the mysterious and complex nature of black holes and their role in shaping the universe. These discoveries are not only deepening our understanding of the cosmos, but also raising new questions about the fundamental processes that govern the formation and evolution of galaxies and black holes. With each new observation, the JWST is providing a clearer picture of the universe's earliest moments and the forces that have shaped it over billions of years.